Hello everyone and welcome to another episode of the Real channel. As you know, we are still on the same topic, PDE, and in today's lesson we want to look at linear operators. If you haven't yet subscribed to the channel, kindly hit or click the subscribe button for me. Now before we start with linear operators, let's look at what operators are. Operators. Now when we talk about an operator, it is a mathematical rule when applied on a certain function produces another function. It is what a mathematical rule which when applied on a function produces another function. Now these operators is not something new, it's something that we have come across way back at the JHS or the SHS level. It's something that we have come across or we've done it at the basic level but in different form. If you could remember at the SHS or JHS level, under the topic relations, functions, and mapping, we look at this particular topic but in different form. So you realize that under mapping, you'll be given a rule and then you'll be asked to find the image of a certain numbers under that particular rule that you have been given. So I quite remember this particular rule that we normally use. And then we'll be given certain numbers. So we'll be asked to find the images of these numbers under this rule, meaning we are going to operate this rule on these numbers. And whenever we operate this rule on these numbers, we are going to get what? Numbers. So this rule operates on numbers to produce what? Other numbers. So let's take the number 3 for instance. When we operate this rule on the number 3, we are going to get what? 2, 3, 6 plus 1, we are going to get the number 7. So this rule acts on numbers to produce other numbers. This is what we learned at the JHS or the SHS level. So at this very level we have gone. So we are going to upgrade or advance to a certain level. We are not going to look at rules that act on numbers to produce numbers, but we are going to look at rules that act on functions to produce other functions. And that is what we refer to as what? Operators. So when you have, let's say, an operator, so we are going to use L to represent the operator, like the Y here. And then this operator is defined in terms of del X plus del Y. We call these operators differential operators. So we call these operators differential operators. Now we want to operate this operator on a certain function. So let's take it that our function is the function u, and this function is in terms of what? X and y. So we have the operator, which is this is the rule, and we are going to act it on these numbers, which is what? The function. So when we operate the operator on the function u, so we are going to get L operating on the function u. This is what we are going to do. We are going to take the operator del X, then we attach the function to it, then we move on to plus. We have del Y, we attach our function u. So the operator L, which is defined as this, operating on the function u, this is what we are going to get del u del X plus del u del Y, which is the same as the first partial derivative of the function u with respect to X plus the first partial derivative of the function u with respect to Y. So you can see that after operating this operator or the rule on this function, we are getting a different function. That is why we are saying that an operator is a rule when applied to a function. A rule when applied to a function produces another function. Now let's look at another operator, when you have, let's say, the operator kill, and this operator is defined as the square the x squared plus the square the y squared, and then we are operating this operator on the function u. So we have the operator operating on the function u. This is how we write it. We are first going to write the operator del square the s square, then we attach our function to it. So we have plus the square the s squared, we attach our function to it. So operating the operator q on the function u, we are going to get the square u the s squared plus the square u the s squared. Let's look at the last one. I'm going to write it and then try to see if you can write it down. So we have this operator m, and this operator m is defined as this. This is our rule, and then it is going to operate on this function u. So we have m operating on the function u. This is how we are going to write it. We are going to write the operator. We have 3 the square the y squared, then we add our function, which is what u. So we have 3 the square u the y squared, then move on to plus, then we write our operator 2 the square the s squared, then we attach our function to the operator. So this is what we are getting after operating the operator on the function u. We are getting this 3 the square u the y squared plus 2 the square u the s squared. Very, very easy. So this is how we write it. Now we can also write it in a very simple form using the partial derivative with respect to x, the subscript one, the one that we learned in our previous lesson, like this, something of this very form, if you remember. So with this, we can also write it in this very form. We have partial derivative of u with respect to x. So our function is what, u, and we are taking the partial derivative with respect to x. So we are going to have u subscript x. Then we have plus partial derivative of the function u with respect to y. So the function is u, and we are taking it with respect to what, y. So if you don't see this and then you see this, it means the same thing. Sometimes you come across this or you come across this. Any one of them is the same thing. Now what about this one? So this, we have second partial derivative of the function u. So the function is what, u, and we are taking the second partial derivative with respect to x. So we have xx, then we have plus the second partial derivative of the function u with respect to what, x. So we have the function is u, and we are taking it with respect to y. Sorry, it's supposed to be y. With respect to y. So this and that mean the same thing. If you don't see this, you see this, it means the same thing. Now what about this? We want to write it in this notation form, this, and then this notation form. We want to write it in this notation form. So we have 3 is already here. So we have 3. Then we have second partial derivative of the function u. So the function is u, and we are taking it with respect to y. So we have y. Then we have plus our constant is there, which is 2, and we have second partial derivative of the function u with respect to x. So we have u x x. Now that we understand operators and how we can operate an operator on a certain function, let's look at what linear operators are. Linear operators. For an operator like this, and then q to be a linear operator, then it must satisfy certain condition. And I'm going to write this condition down. When these operators satisfy this condition that I'm going to write down, then we can say that these operators, I mean m, L and Q are linear operators. So let's look at these conditions. So let's go through these conditions. So we are saying that for an operator to be a linear operator, then it must satisfy these conditions, these two conditions. So we are saying that if C is a constant and L is a differential operator, L is an operator, and then U is also a function, then L operating on Cu should be the same as CLU. If this is equal to that, then we can say that operator, this operator L, is a linear operator. Then we move on to the second condition. So with the second condition, if we are having two functions, and these functions are U and V, and then we have an operator L, and this operator is operating on these two functions. And after doing your algebra, realize that this left-hand side is equal to this right-hand side, that is L operating on U plus L operating on V. Then we can say that the operator L is a linear operator. So this means that these two conditions must satisfy for the operator L to be a linear operator. Now when we combine 1 and 2, and then we have two functions U and V, since we are having two functions, we can also have two constants, and we are using C1 for the first constant and then C2 for the second constant. So when you have an operator operating on these two functions with its constants, then C1L operating on U plus C2L operating on V, this must be equal to that. And when this is equal to that, then we can say that the operator L is a linear operator. So it means that for an operator to be a linear operator, then it must satisfy these two conditions together with that. Very, very easy and then simple. Now we will be looking at more examples in our next lesson, how to verify. Now one property of linear operators that I would like to touch on is this. When you have a differential operator with a constant coefficient, when you have what? A linear operator with a constant coefficient, then we can say that M operating on L should be the same as L operating on M. Look at it very well, commutativity. If you have a differential operator and these differential operators are having a constant coefficient, then we can say that M operating on L should be the same as L operating on L. That is commutativity. So this is what I mean. Let's take it that you have the linear operator L with a constant coefficient. So this is a constant, 3 is a constant, and it is a coefficient of this operator. And then you have another operator. Let's say del x plus del y. Now I can see that these two operators M and L are having constant coefficients. The constant here is 3, the constant here is 2, the constant here is 1, the constant here is 1. So these two operators are having constant coefficients. So when they have constant coefficient, then we can say that commutative property occurs. Then we can say that M operating on L should be the same as L operating on M. Very, very easy. Now another one is when the linear operators are having variable coefficients. Variable coefficients means, let's take it that you have we are going to clean the constant, and then we are going to add a variable coefficient. A variable can be x, and then let's take here to be also y, and then let's use here to be x. Now I can see that these operators, they are having a variable x as their coefficients, and when this happens, we can say that ML is not equal to what? LM. It means when you operate M on L, it is not going to be the same as operating L on M. When The coefficients of these operators are variable coefficients. Very, very easy and then simple. This is linear operators. This is the intro. In our next video lesson, we are going to take examples and then see how best we can solve them. This brings us to the end of today's lesson. See you tomorrow. Bye bye.